Okay, so as Chil was mentioning, I will discuss the main hurdles here of enabling exascale computational chemistry calculations and also path forward to larger scale quantum chemical calculations using exascale computers. My talk is divided in 4 sections. I will give some background of what is exascale and what is its research context, and a second section on the specific challenges for enabling exascale level computational chemistry calculations. And then I will give one of the 2 or 3 ways that there are really to achieve this kind of calculations of this scale, which is what I call a top-down algorithm design. And one specific example of that is molecular fragmentation that I'm pretty sure everybody here will be familiar with. And then I will explain a little bit of how, at a relatively high level, our new algorithms for RTFOC and ORION-P2, which are approaching exaflop performance. Okay, so let's start with some background. This is the website of my group. My group is in Australia at the Australian National University. More specifically, I'm not in chemistry. I am in computer science here at the ANU, and where I lead the high performance computing area. The focus of my research is to design high performance algorithms for the top supercomputers in the world. More in general, I would say this is for computational science, which includes bioinformatics, applied mathematics, and so on. But in particular also, I have some research projects, including GameCCP, which are in the area of computational quantum chemistry. I am one of the PIs of the Games Exascale computing project, and I lead the GPU development for it. And talking of Games Exascale, the results and the work that you're going to see during this presentation, it's mainly due to these people here, 3 PhD students that I co-supervise. They are in Ames with Professor Gordon, Dr. Colin Bertoni, Professor Endler, Professor Gordon. We have other collaborators in the ECP within GameCCP, but that's a specific, the contribution for this work is essentially from these people. Okay, so what's this exascale computing project for those who are not aware of it? This is an effort of the US Department of Energy, which was created to accelerate the delivery of exascale capable ecosystems. This includes the development of the hardware, so the actual supercomputers. One of these is there in the picture here, is this Frontier machine, which will be at the Oak Ridge National Lab. But on top of this, the Exascale project funded a bunch of projects for producing the actual software that will run on these machines to solve the most critical challenges in scientific discovery. And that's really where Games ECP comes into play. The idea behind Games ECP is to build the software capability within games to solve a challenge problem that requires exascale performance. In particular, we selected these unveiling really the catalytic mechanism behind the neutral aldol condensation reaction using mesoporous silica nanoparticles. As some of you might know, this is a potentially huge impact on production of second generation biofuels. But I mean, in general, it will have quite a big impact on the heterogeneous catalysis field. Why does this particular problem require exascale computing? Well, the issue is that we have these pores in these mesoporous silica nanoparticles, which are quite big. And the reaction, you can imagine that there are different potential reactants which are in solution. In this case, as you can see on the right-hand side, there are just 2 examples. One is a desired reactant, which is A, the other is B, it's undesired. So within the pore, which are these represented as these tubes here, there are some gatekeeper groups that prevent B from entering in the pore. A enters the pore, and there's some catalytic groups within the pore. A reacts with these catalytic groups and forms the product which has to diffuse out. Now, the main problem is that it has been shown that this reaction is not cannot be modeled accurately at the DFT level, so it requires higher levels of theory, and also it requires to model the entire pore in solution. Leading to a system size. We have different model systems. The smallest one actually is of the order of 25,000 atoms, which is 10 times larger than ever achieved at this level of theory. So solving this problem will be a major advance in science and in HPC, and it will be the largest ab initio quantum chemical calculation ever performed at this level of accuracy. At the moment, our smallest system is estimated to take 75% of frontier, which will be Exascale, one of the two Exascale machines we are working on, for about 5 hours. Okay, so what are the challenges for achieving these levels of calculations for enabling exascale computation? Well, as all we know, the foundation of quantum chemistry is the Schrödinger equation, and the problem with the Schrödinger equation is that it's essentially unsolvable for complex systems. So what we need to do is to devise, as Dirac recognized in 1929, pragmatic approximations which are predictive without involving too much computation. And giant strides have been done during the last century in terms of solving the Schrödinger equation for larger systems. So let's see how far we got. Here I essentially recast the scale of our calculations in terms of number of atoms, okay? And so the idea is that we are able today at the petascale level to perform accurate quantum chemical calculations on systems of the order of 1,000 atoms. From what we are doing and from our benchmarks on pre-exascale machines, we think that is quite a correct estimate to say that exascale will enable us to reach 100,000 atoms, which is where many systems will enable to explore systems which are very, very interesting from both a material science and a biochemical perspective. What is hindering us? What are the obstacles on the path to exascale? There are mainly two obstacles. The first one is the scalability one, which is a known one, right? Is the fact that the computation required to solve the Schrödinger equation accurately enough tends to scale as a high power of the number of atoms in the system n. But there is another obstacle which wasn't really present until 10 or 15 years ago. I would say 10 years ago, essentially. And this is the inability of many quantum chemistry theories and algorithms, as they are traditionally or were traditionally designed, to use efficiently the novel massively parallel processor architectures. And I will talk a little bit more about these two obstacles. The first one here, the scalability one, can be seen in this table, where I have some of the most used ab initio quantum chemistry methods, together with their scaling, with the system size and their accuracy. Now, from the top to the bottom, we can increase the accuracy of our methods, but what happens as you increase the accuracy, also the scaling increases significantly. What is also very important is that even the most basic method in quantum chemistry, the Artifact method, formally scales as order n to the fourth, which is in computational science, this is a huge, it's a very high scaling. And we really need to get at least to the MP2 level to starting being predictive. So that's the scalability issue. The hardware software issue is a little bit more subtle. So this has to do really with the fact what has been happening in the computational side, the computational hardware level. Until 2007, uniprocessors increased their performance at a rate of about 1.5 times per year. And this has not been true for more than a decade now. The ultimate reason for this failure is that those architectures do not make a power efficient use of transistors, which has become a major issue due to something called the NAND scaling. So as you can see there, from 2008 to 2018, the single core Intel processor performance has not been doing great. So in order to be able to keep increasing our flop performance, so the number of floating point operation delivered per second, we needed to resort to different kind of architectures, which are known as domain-specific architectures. So these are architectures which were designed for performing some specific tasks, okay? So they are not general purpose as CPUs. So they're good at doing some things. And arguably the most successful of these architectures is the GPU one that, as you can see, has been able to increase the flops delivered in a pretty amazing fashion. The problem with these domain-specific architectures is that, first of all, it requires a domain-specific programming model. There's different programming models that you need in order to be able to use the hardware. And for example, this is CUDA for NVIDIA GPUs. And also, there is a major issue in terms of algorithms, because now extracting performance from these architectures requires the programmer to tailor the algorithm to the hardware, as opposed to CPUs, where the CPU was finding for you the parallelism. Here, the programmer has to do all the work. Okay, why am I telling you this? Why is it important? It's important because the way to achieve exascale is to use these architectures, to use domain-specific architectures, in particular for the US machines, its GPUs. So Frontier, for example, will draw over 98% of its throughput from GPUs. CPUs will be there essentially just for flow control. So you have an environment where a piece of hardware really where two different processors live together, the CPUs and the GPUs, and the efficient use of these heterogeneous architectures involves a delicate interplay between the CPUs, in jargon, the hosts, and the devices, which are the GPUs. To give you just a high-level idea of what are the issues that you might face in this kind of architectures, here I'm taking the example of the architecture of a Summit node. So here you have two P9 CPUs here, which are connected to two blocks of memory, this DRAM, and then you have 6 GPUs, each one with their own memory, and they're able to communicate through different paths, really. So you can see here that there are very significant non-uniform memory access effects. But let's zoom a little bit on the relationship and roles between the host and the device. The first thing to note is that the CPU can deliver a flop rate which is way, way smaller than the GPU. So the GPU is about 15 times, delivers about 15 times more flops. So if you want to do computation, you need to do it on the GPU. The other thing is that the CPU has this piece of memory attached to it, which is much larger. It's 256 gigabytes than the one on the GPU. Now, the most interesting bit, whenever you do computation on these machines, you usually allocate your data structures on the host memory because it's larger, but in order to do flops on it, you need to move it to the GPU, which means that you have to go through that NVLink, which is an interconnect between the two, which has a very low bandwidth. What that means is that if you want to do the computation on the GPU, you will have to do much more computation per unit of data than data transfer itself. Another feature is that if you look at the GPU, this has over 5,000 cores, one GPU. This means that achieving those 7 teraflops, those 8 teraflops, requires exposing a massive parallelism for each GPU. And there are 4,608 nodes on Summit, each node with 6 of those GPUs. Okay, so this is just a few more challenges which are related to the quantum chemistry area. The main one is really the theory and algorithms so far have been specifically developed and optimized for execution on uniprocessors or general purpose processors. Typically, when you see parallelism, these are algorithms that are adapted, not tailored to the parallel hardware. They would have a very low efficiency on these heterogeneous architectures if they run at all. So there's very little use of accelerators. We tend to use extremely large data structures with high memory footprint, which is not great because of the small memory that the GPUs have. We tend to have a very heterogeneous workloads, which means that it's difficult to achieve high parallel efficiency. And also the software management is quite challenging. Typically, I am a developer of both games and QChem, and so I can speak for it. We tend to have this mixture of 3 or 4 Fortran versions of Fortran with C and C++. It's not really something easy to manage, to be fair. How do we get then, keeping in mind these challenges, how do we face and overcome them? Well, really the only way is to devise novel computational chemistry methods and implementation that carry reduced computational complexity, but that are able to operate synergistically with throughput-oriented massively parallel hardware. And this can be done mainly in 2 ways. One will be this top-down approach, which correlates perfectly with the fragmentation methods, and the other is the bottom-up. So let's start with top-down. The idea here is that you take a molecular system, partition it into fragments. The properties of the system are obtained by combining the properties of its component fragments. Here you have traditional theory, but really you need novel parallel algorithms which are designed to extract maximum performance when you run the calculation on the fragments. The other approach is that you take the theory and you reformulate it at a fundamental level to expose more parallelism and the lower scaling. So this means that parallelism is exposed at the mathematical level, not physical level. So you're not going to do any fragmentation of the system. And here you need novel algorithms which are tailored to the parallel hardware and applied to the whole system. Now we are going to, GameCCP is much more about the top-down approach, which is what I'm going to discuss now. So in molecular fragmentation, as I was mentioning, you have a big molecule, and this is a model of our MSN pore. You break it into fragments. The energy of the system is recovered by summing over contribution coming from the fragments and the pairing the fragments, so fragment pairs, and the higher order terms. So you can go as high as you want in that expansion, but it has been shown that truncating at the second level is accurate enough. One immediate consequence of this is that if you remember, Artrifoc was scaling as order n to the 4th, but since now we are doing many small Artrifoc calculations on the fragments, this now scales as order n squared, because this is how the number of fragment pairs is scaling if we don't do any screening. So this can be linearized if you don't want to consider fragment pairs that are far apart. Another consequence, so this kind of lowers the scaling, which is really nice, but also another consequence is that exposes a massive parallelism. Fragment and fragment pairs can be computed independently, and that's what we do. We map them to MPI groups that you can imagine as group or nodes on Summit, for example. Now the hard problem becomes to run the calculation on that fragment pair by using potentially many GPUs, which can be in that MPI group, very efficiently. And that's what I'm going to address a little and talk about a little bit in the next few slides. So as we all know, the problem of solving the Hartree-Fock problem is really about forming the Fock matrix, which is the bottleneck. And that formation, which is in the slide, is performed by summing over density matrix elements, which are two index quantities, together with four index quantities, which are the two electron integrals. And this scales as order n to the fourth, but be careful here because this n has a d there, which means that is the number of atoms within a dimer. So that number of atoms will be essentially constant with the system size. Nonetheless, because of the large number of these integrals, the computation of the integrals takes about 70% of the time. And because of the large number, they really cannot be stored and they need to be computed on the fly and then put together with the density matrix to form the Fock matrix. The large number of these integrals is good for parallelism because you can think of parallelizing over the integrals, so mapping them to GPU threads. The problem is that this cannot really be done efficiently. And the reason is that how these integrals are computed. We use recursive approaches where we start from fundamental integrals, the pink one there, combine them together to form intermediates and combine the intermediates together to form the target integrals. And the problem here is that many integrals share many intermediates. So the idea is that you can't really optimize these looking at the single integral, but ideally you want a way to compute groups of integrals together and solving the problem of minimizing the number of intermediates for the group of integrals and not for the single integral. This leads to a way of computing integrals where you compute them in classes or groups, which have wildly varying computational costs from tens to hundreds of thousands of flops. On top of this, you have to solve this non-deterministic polynomial type optimization problem for solving these trees. And it's bad for parallelism because you have units of work which are intrinsically heterogeneous. On top of this, there are design constraints, as we said before. We will need to compute order n to the fourth integrals. This must be done on the GPU because where the flops are. Now, in a situation where we want to compute these integrals, we really don't want to compute them and transfer them back and forth across the host and the device, because that would mean that we are running at the speed of the NVLink, which is many times slower than the rate with which we can do flop on the GPU. On top of this, we have 5,000 cores on the GPU, and ideally we want all those cores to do exactly the same amount of work so that the parallelization is balanced. We can think perhaps we could do this by treating the integrals in batches which have the same flop cost. On top of this problem, remember that we have more than one GPU, we have many GPUs, and the workloads must be balanced across the GPUs as well. So one way to think about that is if we batch the integrals in units of the same cost, in classes of the same cost, we could then distribute those batches using dynamic load balancing across the GPUs. I will talk briefly only and address the first three issues for the sake of time. So the key here is to realize that each of these integrals is generated by coupling data from two index quantities, which I called alpha, beta, and gamma, delta, as illustrated in, and you can think of that as a big matrix, right? What's interesting about the two electron integrals is that their flop cost is really factorizes in a term which comes from one pair and a term which comes from the other. So what we do is to form a container with batches of these alpha beta quantities which have all the same cost. So each batch is in a bin which has the same cost. And we form these on the host, on the CPU memory, and this requires order n squared work. Now, what we can do then, once we formed this batch container with all the information that we need, is to transfer that across to the device, which will require only order n squared transfer. Okay, now once we are on the device, we have all the information that we need to compute the integrals. So all we need to do is to compute to pair two batches and compute the integrals. These batches tend to be quite large. So if you look at our typical size is of the order of 2,000 pairs. And so the batch of integrals that you're going to form is the tensor product of the two batches. So we're looking at the order of 4 million integrals each time. And each one of these integrals, or actually classes of integrals, is mapped to a thread. And which means that you're doing 4 million classes, each one on a thread with perfect load balance, because they use the same code and they have the same flop cost. Another interesting consequence of this is that overall in the algorithm, we did only order n squared transfer, and all the order n to the fourth computation is done precisely on the GPU. So that transfer, we don't even see it because it's so tiny with respect to the amount of computation that we do on the data, that we are running essentially a peak. Okay, so how does this perform? These are results that we obtained on Summit last year. We presented at Supercomputing 20. We selected 3 systems just to benchmark our approach. Around 2,100 water molecules, 9,100 and 20,000 water molecules. Now, these systems were fragmented, and then they were run at the MB2. So we treated all the dimers explicitly, no dimers screening, and we ran on Summit by increasing the number of nodes. Be aware that each node has 6 GPUs, so you can find a number of GPUs at the top. Now, with the system with the 2,000 water molecules there, we reach a pretty good parallel efficiency on around 256 nodes. We get a speed up of 240 times with respect to one node. Then increasing the system size, we get to this 9,100 water system, so about, well, that would be 30,000 atoms. And we reach a 60%, well, the parallel efficiency is pretty high until 1,024 nodes. And but it starts flattening off and reaches 60% when we are using 4,096 nodes, which is 24,000 V100. The reason why that happens is that because this system really becomes too small for running on that number of GPUs. In this system with 9,000 water, we have about 7,000 fragment pairs, which if each pair is mapped to a node. So what you have to think is that some nodes at that moment, when you use 4,000 nodes, are getting 1 pair and some are getting 2. So it's a very unbalanced situation. So what we did is to increase the system further, and we went up to 20,000 water molecules, which is 60,000 atoms, all treated at a quantum mechanical level. And we reach a 91.3% accuracy on 26,000 GPUs, which was a huge calculation. This took about 2,200 seconds on this number of GPUs. We are today able to do this because we improved the algorithm in less than 10 minutes. How about the performance of this algorithm? You know, each pair is mapped to a group of nodes. So how does it perform with respect to the number of GPUs within that node? And that's what this plot is showing. So we have a fragment here, so a single fragment, which is 200 water molecules. And we run the calculation from 1 using up to 12 GPUs, and we measure the speed up with respect to 1 GPU. And so on 12 GPUs, we have a 94% efficiency, which is extremely high. On 6 GPUs, the efficiency was 97%. And that's what the dotted line dashed line, sorry, is showing. That's the configuration that we chose for all the previous calculations that you have seen in order to maintain a very high flop performance. Okay, so how about this performs against state-of-the-art codes? This is a plot that we have which measures the speed up of our code against Terrachem, which is the state-of-the-art code that has been the fastest so far. And so what we do here is to have this chain of glycines and RNA residues. The glycines go from 213 to 848 atoms, the RNA from 387 to 1,155 atoms. So we increase the size, and what the red bars are showing is the speed up that we obtain when we run our code on one GPU against a Terrachem running on one GPU, while the blue ones show the speed up that we obtain when we run our code on 8 GPUs, but also Terrachem on 8 GPUs. So it's a fair comparison. Now we can see that we get increasing speed ups with respect to Terrachem as we increase the system size, because the way really our algorithm is designed is that we like to treat larger systems, but also our code is much more scalable. So when we use 8 GPUs, we observe pretty amazing speed ups all the time with respect to Terrachem. So that's STO3G. Very similar story for 6G1G. What's more interesting probably is in this table where we have the number of basis functions that we used, but also we have the speed up if you want to measure ideally with respect to games running the OpenMP version. We stopped here at glycine 60. So here games is running on 42 cores of the IBM P9 processor, which is an amazing processor. So it's running in parallel on one CPU. So it's one CPU with all its cores against the Volta. And so here you see 626 seconds, and we are taking instead 7.8. So it's a big speed up. We also measured with respect to this quick program. If you look at the glycine 110, we are taking 24 seconds and they are taking 250, so it's a 15 times the speed up, considering that they're using the same GPU. Okay, quickly, you can say Hartree-Fock, what do you do with Hartree-Fock? Nothing. So we need to add the MP2 really here. As people may know already, the MP2, the complication boils down to this formula. We have these 4 index tensors that are used to accumulate the energy in this formula, and at the bottom we have the molecular orbital energies. Mainly the issues of the classical MP2 method rise because you have order n to the 4th of these tensor elements, which are really 2 electron integrals over the molecular orbitals. And each one of them requires all the integrals in the AO basis. That's really the origin of the issue. The algorithm, the classical algorithm, the most used is the Head-Gordon semi-direct algorithm. It's quintic, so it can be done very smartly. But the issue is that they need to store order n to the 4th elements. And so this requires that there's no memory really that can contain that. So you need to store them on disk. Then you need to retrieve them continuously. This is a big issue for parallelism and for efficiency. So the way really to tackle this and to do this a bit more efficiently, today we know this already, it's to use RIMP2 by using a low-rank approximation. What people do is to take that tensor here, which is a 4-index quantity, and approximate it with the sum over 3 and 2-index tensors. Now, you see a different n here, which is the nx. This is the size of the auxiliary basis set. As long as that is large enough, this approximation is extremely good. So what happens now is that the AO to MO transformation can be done on these three-dimensional tensor. And then, as you can see, we need to form this B intermediate as well, which is another tensor contraction, then form G as before, and then once formed the G, we can accumulate the energy. Now, what I want to really discuss here is that, first of all, now the AO to MO transformation is no more the bottleneck. So it's order n to the 4th flops. It has a way lower memory requirement. It's cubic in memory. But on top of this, what's very, very nice about this method is that the most expensive steps, which are these three, the D, B, and G formations, they are recast as matrix multiplications. And those can run at peak performance. Unfortunately, one of the problems for heterogeneous architectures is that order n cubed. That is a memory requirement which is way too big for the GPUs. So you can imagine that you have to store those on the host and then move the blocks back and forth between the GPU and the CPU, and that requires quite efficient algorithms. Here, I just give a very small example of how we do the formation of G and accumulation of energy. What we do is to create a queue of occupied orbitals. These are more occupied pairs, which I called with those curly I and J. These are simply sets of pairs of integers, right? They represent the map to the molecular orbitals, the occupied orbitals. We distribute them dynamically across the GPUs, but the problem is that the D and B matrices are on the host. So based on the batch indices, we move blocks of those D and B tensors to the GPUs. Once we have two blocks there, we can form a block of the G tensor by multiplying those two blocks of B and D. And once we have G, we can start accumulating. We do a first accumulation where we sum over the virtuals, and we form this array of energies EIJ that then we further sum until we get a scalar value. And then we can reduce the scalar values across all GPUs. Here's some preliminary results which are unpublished yet. I hope they will be soon. We benchmarked the new RIMP2 algorithm by, what we have here is all calculation done with 631G star, CCPVDZ, RI fit. And we ran on these systems the first table is measuring our wall time against our previous wall times, or not really mine, the previous implementation in LibChem, which is this C++ library, which is in games, which is at the forefront of the development for game CCP, and against LibChem running on GPU. Again, CPU there means in parallel on 42 cores. So we measured a pretty amazing speed up as well. So our new algorithm does really well, even compared to what the library was doing before. What's more interesting is that we managed to obtain quite an amazing result here. We ran the entire fragmentation, and this includes the SCF time. So it's the entire thing, SCF plus RIMP2, using this basis set on these essentially protein with a sequence of 4 amino acids repeated 500 times on the entirety on Summit. This was over 30,000 atoms. We correlated over 120,000 electrons, and this ran in less than 3 minutes on the entirety of Summit. The calculation with that basis set, the auxiliary basis functions were over 1,273,000. And this was 15 times more larger the system and the number of electrons and basis functions than the previous world record. So this is kind of still a bit confidential because it was submitted for publishing. So we waiting for May to hear the response. Here is just a feature of game CCP. We performed the largest calculations. We are really at the forefront of the ECP in terms of quantum chemistry. This year, again, as I showed you, the largest MP2 level calculations. We are now porting our code to Frontier.